Right, in this lecture, we're going to move a step further into considering what instantaneous acceleration is. In our previous class, we talked about instantaneous velocity, and we saw that instantaneous velocity is just taking derivative of the displacement. Okay, so if you have a particular equation represent the displacement of a particle, and we decide to take the limit of that particular displacement, then what we have is the instantaneous velocity. Okay, so just like we have in instantaneous velocity, we can also have instantaneous acceleration, and instantaneous acceleration is simply the limit. It is the limit of the change in velocity to the change in time as the change in time approaches 0. Is that okay? So when we take the limit of the change in velocity to the change in time as the time approaches 0, then we call it the instantaneous acceleration. Okay, so it is simply the full differential of the velocity. Okay, so just mathematically we can represent it using this format, and a very likely exam question is, they might ask you that what is the implication of the limit of the ratio of the change in velocity to the change in time as time approaches 0. Of course, the answer is instantaneous acceleration. Okay, so this implies that if velocity is the derivative of displacement, and we say that acceleration or instantaneous acceleration is the derivative of velocity, it then shows that the instantaneous acceleration, let me use IA to represent it, instantaneous acceleration is the second derivative of the displacement. I'm sure you understand why I said so, because we said that the V, the T is acceleration, right? If you look for the derivative of velocity, you get acceleration. But we said that the x dt is equal to velocity. So if I take the second derivative of displacement, then I'm going to get my acceleration. So mathematically, we can say that instantaneous acceleration is equal to d square x over the t square. T is also a likely exam question. So having considered that, let us take an example to illustrate what we have just said. We're told that the particle, a particular body or a particle, has the equation illustrated just on the screen. We have x is equal to 4x raised to the power 3 plus 3x squared at time t equals 1 and time t equals 2. Our task is to look for the instantaneous acceleration. But because we already said that instantaneous acceleration is the second derivative of displacement, so our task here is to look for the second derivative of the displacement and then substitute the values of t equals 1 and t equals 2 in the equation. Okay, so we can have our solution to be, since x equals 4x raised to the power 3 plus 3x squared, and we said that acceleration is equal to d square x over the t squared. That is the second derivative of the displacement equation. So looking for the first derivative, we can have the x over the t, which is equal to v, is equal to, from the formula method in differentiation, we have 3 times 4 raised to the power 3, 4x raised to the power 3 minus 1 plus 2 times 3x raised to the power 2 minus 1. And I'm sure you still understand or remember how we came about this. We said if y equals x, then the y dx is equal to, let's say, x raised to the power n. The y dx is equal to n times x. Then you reduce the power of n by 1. And that is what we have just done over here. So if we have this, we say this is 12x raised to the power 2 plus, this is 6x. 2 minus 1 is equal to 1. So, and x raised to the power 1 is still x. That's why we have 12x squared plus 6x as our velocity, or the first derivative of the displacement equation. Okay, but this is not our focus because we're looking for the instantaneous acceleration. So we have to differentiate this term again. We have to differentiate this again. Is that okay? So we have dx dt d square x over the t square would now give us 2 times 12x squared minus 1 plus 6x raised to the power 1 minus 1. You know, anything raised to the power 1 is that particular thing. So x raised to the power 1 then minus 1 will give us x raised to the power 0. So this gives us 24x plus 6 as the acceleration equation. Okay, but we were told that when x is equal to 1, what is the instantaneous acceleration? So at x equals 1, all right, so we have a will be equal to 24 into 1 plus 6. That is, whenever I see x in the instantaneous equation, I would have to substitute the value of 1 into it. Okay, so we have a will be equal to, let me demarcate this a bit so that, all right, so this is what we have. So we can say that a will be equal to 24 plus 6. And 24 plus 6 is 30 meters per second squared. Remember, it is acceleration, okay? 30 meters per second squared. Now, at x is equal to 2, what then is the value of our instantaneous acceleration? We have a will be equal to 24 into 2 plus 6, right? So this is going to give us 48 plus 6, and 48 plus 6 is equal to 54 meters per second squared. So when x equals 1, the instantaneous acceleration for this particular body or for the particle is equal to 30 meters per second squared. Why? When we change the value of x, and in this case x is equal to t, so take note, let me even write it down somewhere. Note, x is equal to t. So this we can replace it by t. So since I already penned down this int, so wherever you see x, you put t equals 1 into it, and then we have what we have on the screen here. So with this, I'm sure you've understood what instantaneous acceleration is and how to solve problems pertaining to instantaneous acceleration. This is where we'll draw the curtain for today's class. So see you in our next class where we will discuss more interesting concepts in physics. See you in the next class.